My name is Tina Zhang. I come from Intel Open Source Technology Center. I am a software engineer and work on GPU virtualization. Currently, I'm working on a GPTG project, which is Intel's full GPU virtualization solution. Then let me introduce this topic. So this session is basically about how to share buffers of a mediated device with the host side. We propose a generic buffer sharing mechanism for mediated device to share their buffers. With the help of this mechanism, mediated virtual GPU can expose this frame buffer as a standard DMBuff object to the host side. So this mechanism is originally designed for GPU virtualization, but it is also general enough for other I/O mediators. Here is the agenda. So we only have 4 parts here. In the first part, we are going to talk about the background and the motivations. The second part is about the design of the buffer sharing mechanism. The third part is the status, and the last part is a summary. So today, as we know that VFIO mediated device work is the cornerstone of enabling shared GPU virtualization usages among VMs. VFIO is a secure user space driver framework which can directly assign a physical I/O device to VMs. Mediated device framework utilizes VFIO framework, which can be used to mediate a physical I/O device into several virtual mediated devices, which can be assigned to VMs. It also provides the user interface for management, which can be leveraged by the libvirt. So software built on libvirt can create and configure a mediated device. Each mediated device has a unique UID. Then after the user passed the mediated device UID to Qemu, this mediated device can be attached to the Qemu process and used by the VMs. Mediated virtual GPU is a kind of mediated device, which provides GPU virtualization for VMs by sharing a physical GPU. While the VFIO mediated device framework provides a general mechanism to implement a mediated device, there are still device-specific problems which require new extensions. A key usage requirement in GPU virtualization is to render guest frame buffer in the host side. The first scenario is in remote virtual desktop or maybe cloud gaming. The remote display protocol, for example, SPICE, needs to directly access the guest frame buffer and stream it to the remote clients. The second scenario is about the automotive virtualization. Host GPU mediator may directly configure guest frame buffer to the local display panels. The third scenario is in client. A host compositor may map the guest frame buffer into surface, which can be composited into some fancy effects through OpenGL. So those are the usages for GPU virtualization. Other mediated devices may also have the requirement to share their buffers with the host side. So that's why we want to propose a buffer sharing mechanism to mediated device. And next part, we are going to talk about the design of the buffer sharing mechanism. So the design aims to provide a generic way for hosts to access the mediated device buffers. In order to achieve it, we choose the solution based on DMBuff subsystem. The DMBuff subsystem provides a framework for sharing buffers for hardware access across multiple device drivers and the subsystems, and for synchronizing asynchronous hardware access. It's the generic way provided by kernel to share DMA buffers, and has already been supported by many device drivers. Besides, in the user space, it is also supported by the Linux graphic stacks. For example, EGL has an API to create an EGL image according to the DMBuff file descriptor. And this is also used by remote protocol, for example, SPICE. Considering different kinds of MIDI device may have different buffer sharing attributes, a set of APIs is proposed by different MIDI device in the same category. As a case study, we implement a set of APIs for MIDI virtual GPU to share its buffers and for virtual GPU to talk with the user space clients. Okay, then before we go into the implementation details, let's give a short review of DMBuff. So there are mainly 3 components. The buffer exporter, the buffer user, and the DMBuff itself. So the DMBuff object is actually a SG table, which keeps a scatter list to save the DMA address of the buffer. If we only consider the simple use case, the buffer exporter is usually a buffer producer. It needs to implement all the DMBuff operations and expose the DMBuff as a file descriptor to the user space, which can be sent over Unix domain sockets to be shared between applications. The buffer user imports the DMBuff object and gets the scatter list in the SG table. So after it maps the buffer address to its own address space, then the buffer can be used by the buffer user. That's the way the standard DMBuff subsystem works. So here is the architecture picture of our proposed buffer sharing mechanism. The mechanism mainly works as the buffer exporter, and all the others in the host side, in the kernel space, which would like to use this buffer, are working as a buffer user. These blue components are brought in by the implementation of this mechanism, including the APIs defined in MIDI device framework and all these stuff things in the specific MIDI device driver. So MIDI device driver need to manage and implement the DMBuff operations of the MIDI device buffer. And SG table management needs to decide the buffer location place where the buffer is actually allocated. The exposed pages can be wrapped into some device-specific objects, managing the details of buffer allocation. So when a user want to get exposed MIDI device buffer, it needs to first to query the use this API to query the buffer information. This IO control can also be used to check whether the MIDI device driver is ready to expose buffers. After the first API is returned successfully, the user can invoke the second API to get to ask the MIDI device driver to create a DMBuff object and install a file descriptor with it. And at last, return the file descriptor to the user space. Then the user space applications may send this file descriptor to the real user. And with this file descriptor, the buffer user can directly, first, of course, it needs to map the buffer address to its own address space. Then it can directly access the buffers. So specific to our mediated virtual GPU, we propose two APIs. And this is the first one, graphics plan. Actually, this API is used to return the information of the frame buffer. We have several types of frame buffer. Currently, we support cursor plan and the primary plan. So user needs to tell the mediated device driver which plan it wants. Then the mediated virtual GPU driver can return these informations to the user space. And the DMBuff ID is the most important one, which is a token of a frame buffer and going to be used in the second API. So this is the second API. With the DMBuff ID as the input parameter, this structure can return the DMBuff file descriptor of that DMBuff. So then let's come back to our scenario, our usage scenarios. In the remote desktop, with the help of this mechanism, Qemu can get a DMBuff file descriptor of the exposed guest frame buffer. Then it passes it to the remote protocol server, for example, SPICE. With the file descriptor, remote protocol server can directly access the exposed guest frame buffer and stream it to the remote clients. For the automotive scenario, similarly, Qemu can get the DMBuff file descriptor with the help of this mechanism and pass it to a display switcher. A display switcher is actually user space applications, which can use the libdrm KMS APIs to directly control the local display panels. So with the file descriptor, with the DMBuff file descriptor, the display switcher first needs to call this DRM prime FD to create a buffer handle according to the DMBuff file descriptor. Then he can use the mod add FB to create a local frame buffer object according to the buffer handle. And at last, use the mode set control to render the guest frame buffer to the display panel. So in the client side, again, Qemu can get the DMBuff file descriptor with the help of our mechanism and send the file descriptor to the host compositor. The compositor can first use this EGL create image to create an EGL image according to the DMBuff file descriptor, and then use the GL bind texture to bind this image, EGL image, to a texture. After the exposed guest frame buffer being banded to a texture, the guest frame buffer can be composited into some fancy effects through OpenGL by compositor. Here are some implementation details. We don't want to list all of them because many of them are related to the DMBuff supports. Just three items here. So first one is the DMBuff management. As a buffer exporter, we need to implement all the DMBuff operations. When a user in this user space asks for a DMBuff file descriptor, we need to create a DMBuff object and install a file descriptor with it and return the file descriptor to the user space. Here we need to pay attention to the reference count of DMBuff. We need to make sure that when this DMBuffs, when all the file descriptors of this DMBuff object are closed by the user in the user space, the DMBuff object can be released timely. Some mediated device driver would like to cache the exposed DMBuffs. The benefit is with cached DNBuff lists, media device driver doesn't need to create a new DNBuff object with each time the user asks. It can just scan the cached list to see whether there is an old one can be reused. And this can also benefit the user space, as a user also can reuse the old resources according to the older DNBuff object. The SG management, SG table management, including creating, using, and releasing SG table. We need to pay attention to the buffer address, as this address may be decoded from some guest shadow page table. So the host needs to translate, the mediated driver needs to translate it to the host address space before using it. And the last one is the information collection. Media device driver needs to get this information by decoding the values in the media device virtual registers. And here is the current status. Our implementation for Intel virtual GPU patch is sent out, and then the latest version is 15. It is tested with Linux kernel 4.13, and we are working with the community for the upstreaming work. And besides the user space, Qemu UI also have 2 patch sets to use the mechanism, and they are both designed and implemented by Gert Hoffman. Okay. So here is the summary. We believe the design of the proposed buffer sharing mechanism is generic enough for I/O mediators to share buffers with host side, as we choose the solution based on DNBuff subsystem. As a case study, we implement this mechanism for mediated virtual GPUs. And then we would like to see that all kinds of mediated virtual GPU would be aligned to leverage the proposed APIs and the buffer sharing mechanism to expose guest frame buffer to the host side. And at last, we welcome innovations based on this generic buffer sharing mechanism. Yeah, again, this is our GVTG repo. You can access it and to get the idea of Intel's full GPU virtualization solution. You can get the latest information of our work there. We also have a wiki for users to try and deploy the solution. We hope you can have fun with it. Thank you.